Hi out there. I'm trying to revitalize some work I was going through in the past. So because of that, I made a small little effort to look at some slides. I gave it a talk last year at the Copper Mountain Conference on Iterative Methods and wanted to go through them. So the topic is dynamic non-uniform randomization and asynchronous linear solvers. Okay, outline for the talk. Go through the motivation. Why does anyone care about this method? Why do I care about this line of research? What are we considering doing? What results do we have? And what am I going to do going forward? The goal for this was really to emphasize motivations. So that's where a lot of the modifications from the conference talk were made. The results are very brief here. Don't really go into any details. There's a couple links. It's pretty much what I said on the outline, just that this is a slightly extended, more modified than truly extended version of a talk given at Copper Mountain, and I really tried to motivate the beginning. Okay, so like a lot of the talks that were given at any conference on iterative methods, but especially at Copper Mountain, one of the main goals is to solve a large linear system. And for anyone that stumbled across this talk, there's probably no surprise there, but a natural question anyone should ask themselves for any research topic is, why does anyone care? Why do I care? So the reason I care about linear systems is they really are prevalent everywhere. They come up in so many different applications. They're ubiquitous across a lot of science and engineering. My personal experience and desire to learn more about them kind of stemmed from computational fluid dynamics. So taking the PDEs that help govern fluid flow in our simulations, and you discretize them, you end up with a large linear system, and you end up using some version of an iterative method. So how is this typically done? How do we typically solve large linear systems in practice? Not necessarily in research, but out in production software. And I would say that that's often done with projection-based methods. So the most popular of those are Krylov subspace methods, things like conjugate gradient or GMRes. What's different here? So this whole avenue of research is really looking at what I would describe as a fine-grained linear solver. So examples of those are Jacobi and Gauss-Seidel. The idea in fine-grained techniques is trying to get a higher utilization rate out of your parallel architectures. So the methods themselves may be a little less efficient, but hopefully you can get such higher throughput that you kind of overcome that deficit. Although realistically in the future, we're going to look at using modified versions of these techniques in conjunction with Krylov solvers or other projection methods. So for example, as preconditioners, possibly inside of a multigrid technique. Okay, so again, what am I trying to get out of the research? What is anyone trying to get out of this research? So one goal is just to look at trying to find a way to know when the technique's going to terminate. So we're not solving problems at scale directly. We're doing everything iterative. So we start with a guess and we get a little closer and we get a little closer, and this goes on and on and on and on. And it would be nice to know when that might terminate. So not necessarily I set a max iteration count of 500 or 1,000 or whatever the case is, and I know it'll terminate there, but when am I actually close enough to the answer I want to get to? So there's been some research starting maybe way before this, obviously, but the randomization techniques that we're considering here kind of started in 2010, 2012, 2015. So there's 3 papers there that I'm calling out specifically as kind of seeds for this research. The first is by Leventhal and Lewis, the next by Greedily and Oswald, and the last by Avron, Drurinsky, and Gupta. The underlying idea for all of these techniques is that by balancing the work, by using randomization to change which processor is assigned to which bit of work you can start giving better statements about how much closer we're getting with each iteration. So on average, how much does the error decrease each step of the way? And that's very valuable because if I know how much it decreases and I know what it starts at, I can set a tolerance, and before I do any calculations, before I start running on my supercomputer, I can know how many iterations it's going to take to get me to where I want to go. Okay, and the other obvious goal for numerical methods research is just to make things go faster. So alternatively, on these similar kind of techniques, looking at fine-grained methods still, there's been a couple papers by Wolfson, Pao, and Chow that looked at a Southwell-like approach, which we'll get to find a little better later, but I think the overall idea is just to think of it as a greedy algorithm. So my iterative method is dividing the problem up into a bunch of small pieces, which is where fine-grained is coming from. And the Southwell-like idea is that I want to be greedy. Instead of just picking the first piece that was cut up or the randomized piece that was cut up, I want to pick directly the biggest piece in some sense. All of the techniques tend to divide the work into equal parts, but not all of those parts have the same contribution to the remaining error. So the motivating question for all of this research is there a way to combine the natural greediness of the Southwell-like approach with the randomized and possibly asynchronous nature of the solvers that were proposed on the last page? Okay, so now I want to get into what are we considering? How are we looking at solving this juxtaposition problem? So to set the stage, everything we're considering is some variant of block asynchronous Jacobi. So we're taking our large linear system, we're cutting it up into blocks, which effectively is almost rows. And we're taking each chunk of rows and executing them asynchronously. So each processor will work on one block of rows at a time, but it doesn't have to wait for the other processors to finish. Once it's done, it can go and grab another set of equations to solve. As I brought up at the very beginning, realistically, these solvers are going to find their truest final form as accelerators or preconditioners for other methods, so not necessarily where they're being used by themselves. However, just to kind of compare them with each other and with other methods of a similar nature, it seems more fair to just look at them solving systems directly, which does limit the problems we can look at, but makes it a lot easier to make an apples-to-apples comparison and to see what effect our research is having. So I wanted to go over kind of the approach that we're trying to take, keep hinting at that motivation, why we're thinking it might work, look very, very briefly at some numerical results, and then talk about where to go from here. This is the only math-oriented slide I kept in the talk, I think. And I'm just trying to set the stage. So we're taking a large real matrix, letting it be symmetric and positive definite. So in some sense, it's just a nice matrix. It describes a nice problem. Then we're going to make updates based on finding a residual. So how far away is our current guess? Finding how far we should step in the direction we want to go, which is based on how much error there is. And then updating our guess by going forward in that direction. So here D is our direction, gamma is our step size. So at this point, there's no clue what a direction vector should be. Historically, in the very traditional Jacobian Gauss-Seidel, those direction vectors are just taken to be the coordinate direction, so your x-axis, your y-axis, and so on and so forth. So those are traditionally denoted E sub I. So we're going to take, in this setup, we're going to take our direction vectors to be our coordinate directions with some probability. And that probability is going to be that it's weighted to select more frequently the components of the problem that have a larger diagonal element. So in our linear system, in some sense, we're trying to select the parts of the matrix that are bigger as judged by their diagonal element, which is a fair way to think that you might be solving more important parts of the problem. So we're just finding a discrete probability distribution based on that. And if we do that, this result, which is taken from the Avron paper, but there's similar results in all of the papers. In fact, they might all have the same result, is that the expectation in the A norm of how far away my current iterative is from my final solution, so how much error is there left, is some multiple of my initial error. So there's a typo. There should be a star on the leftmost x. And that's really nice. That gives us a multiplicative reduction. So every step we're getting some factor closer than we were before. And that factor is calculatable very simply by looking at properties of the matrix itself that we're starting with. So for every problem I have, I can get some estimate of how long it's going to take me to get to my solution. Okay, so if I try to genericize that algorithm a little bit more, I'm going to say that I'm going to loop through all my processing elements. So each core of my node, or each processor I have, and then each one of them is going to loop through independently. And this is where that kind of asynchronous nature comes in. They don't necessarily have to all group back up. Each one is doing its own iteration. So the first thing it's going to do when it starts its for loop is to pick a component of, in the block sense, some component of rows, some group of rows, or a single component, and it's going to do that somehow. So in the last example, it was picking it based on that discrete probability distribution. However, we really want to motivate that to be something a little greedier. It's going to read the corresponding entries that it needs to make the calculation, perform the relaxations for those equations, and then update the data. So the next time it goes through, it's going to get the updates from every other processor that finished. So the goal is to make this component selection random, and we're doing that to balance the computational load and to hopefully get more results in expectation about how much the error is being reduced each time. We want it to be greedy, so we're trying to get something that selects a component that helps us reduce the error as much as possible. So we're doing that, we're making a Southwell-like estimate, and we want it to be a net dynamic. And this is stemming from the fact that we believe that what defines greedy can shift over time. So if we go back one slide, this distribution is defined before the problem starts. It's a reasonable distribution. It's probably a step above just taking a true uniform distribution, but there's no information from the problem incorporated into it as it goes. And it seems like there should be a way to if you have 1,000 iterations in your problem, maybe every 100 iterations you revisit what the probability distribution is. And doing that, maybe you can accelerate convergence. Okay, so when we try to mimic this Southwell-like approach, the Southwell algorithm itself looks at individual contributions to the residual. So when we look at the residual of b minus a times x, so how close is my current x to solving the equation, I can look at the contribution for each row to that. If I do that, hopefully I can find some way to take those local residuals and use them to make a probability distribution. So the first thing we did was just look at a very simple matrix that comes from a finite difference discretization of a 2D Laplacian on a small grid. This isn't a representative problem of anything that I'd want to solve at scale necessarily, but it's kind of in family, and it hopefully was going to give us some insight into what we should look at and how we should be forming these distributions. So on the left, we have unsorted residuals, These are just normalized against the largest local residual. And it just looks a lot like noise. But when you sort them from highest to lowest on the right, you see that there is some order. And if I was to pick one of those components to update, I would not want to pick anything at the far right of the picture. I'd rather pick one of the components on the far left. It's worth noting at this point, I think, that in practice, the number of components is going to far, far outweigh the number of processing elements. So if there are possibly 1 million components, you might have 100 processors doing the update. So if they're selecting randomly, I really don't want them to be selecting random uniformly and updating components that have very little contribution to the residual. I would rather reduce the residual most on the components that need it the most, so on the left of that slope. So when we look at this slope, what comes to mind is fitting a continuous probability distribution to it. So historically, this work has either kind of gone the path of taking uniform distribution or looking at a discrete distribution defined by something you know beforehand. Here, we're looking at taking the residuals, sorting them, and then fitting a distribution to them. So this is using exponential distribution, and the more steep, so more like the black line, we're getting closer to a true Southwell approach where we're selecting only the component that contributes the most to the residual. And if we draw from the red line, we're getting closer to the uniform. So there's some balance here because we want all components to get updated, but we want to get as much of the greediness as we can. Okay, so another aspect to our approach is that we want to make this random selection change dynamically. So, like I said, we're trying to select the right residual components in the similar sense to the classical Southwell. But we don't want the large computational overhead of every single update. We stop everything, sort them, and pick the single largest contribution to the residual. So I don't always need to pick the farthest leftmost component on that last graph. So the way we're trying to address that is we're going to monitor which residuals or blocks of residuals contribute most to the global residual, and then periodically rank them and fit a distribution. And the periodicity is really a driving factor in this. So it's a matter of not outweighing the benefit you'd be gaining by selecting components more appropriately or more greedily in all the extra computations you're doing to figure out how to do that. So like I said, historically, at least in the papers we've examined, if randomization is used, it tends to be used either make a uniform choice, so pick any component, and the benefit there is you are really kind of load balancing. So especially in a distributed scenario where you might be running on different forms of computing architecture, maybe you have some GPUs, some nodes made up strictly of CPUs, anything, you're balancing the load between everything. Taking a discrete distribution defined by the ratio of diagonal element to the trace. So again, this is picking the largest element in the sense of how big is your diagonal element. And there has been some work done towards defining randomized greedy picks in the Griebel and Oswald paper in particular, but they didn't go through the practical use of that as far as you'd like. It was more looking at the theoretical aspects of if you could pick something that was sufficiently close to a Southwell approach, how would that benefit you? So the main two ways we wanted to consider doing this were, start at the bottom first, was to fit a continuous probability distribution to the sorted local residuals. So we played with exponential and triangular. Or to look at a discrete distribution defined by the ratio of local residuals to the sum of all the residuals. So this is, in effect, doing something very similar to the trace to size of your diagonal element, in that I'm trying to define a discrete distribution that can be updated dynamically, or it could not. This is something I could do once at the beginning, or I could do it periodically. So this is going to be less expensive, but probably less of a directly good fit. Okay, just a couple slides on numerical results. That's really not the emphasis of the talk here. The real question is, how much can we improve performance by selecting an appropriate component? And the kind of obvious sub-question there is, how much overhead do you introduce? So we'd really expect that if we're picking components more intelligently, we're going to accelerate how many iterations it takes to converge. However, we're also, in some sense, adding overhead to the iterations or raising the cost per iteration, depending on how you calculate things. But there's a trade-off there, and we're really trying to find a good balance. Okay, so here's some results, again, for more or less that toy problem we looked at initially. And this is just looking at if we have true Southwell or we have a fairly sharp exponential distribution. Those results are very much in family in terms of how many iterations it takes you to reduce your residual appropriately. If we look at Jacobi, so traditional Jacobi, not asynchronous Jacobi, compared to uniformly selecting your components, those are more or less in family. You actually do a hair worse with uniform. But really, the point of this was just to show that on this toy problem, in our simple example, we're kind of seeing results we'd more or less expect. So if you just pick things uniformly, you're going to be on par in some sense with your traditional fine-grained methods. And if you were to instead use the exponential distribution that's weighted to be more Southwell-like, you're going to be in family with Southwell. So all this really did was give us some confidence that things are behaving like we think they should. If we go forward again to a slightly larger scale, so this is still looking at the 2D discretization of the Laplacian, but this time we're on a much larger grid, and we've parallelized on essentially a shared memory device, an Intel Xeon Phi, 64 cores, on one of the high-performance computing clusters at Old Dominion University. So here we're dynamically updating our distribution every 5 iterations. So the dashed red line is the performance of uniform, and then we have a bunch of different exponential distributions. So they are taken at several different parameters for your lambda. Everything was run multiple times, and these are averages for those runs. So what we're seeing here is that just in terms of time of execution, the parallelized exponential runs are doing better, except for the most uniform-like exponential distribution. So in that sense, we're getting too close to the uniform, and we're introducing overhead that's surpassing what we're not doing in the uniform. So in the uniform, we're not going through the hassle of ranking and updating a distribution. And this is much more encouraging. This is kind of showing that we are doing better when we're doing our more dynamic, greedy, randomized approach than just doing a pure uniform approach. And here's just punting to a couple of papers that we had in 2019 and 2020. We have plenty more numerical results. We also did some work looking at blocking and how to block appropriately for these methods. There's plenty more to do, but there was some preliminary work already published. Okay. So the summary is that I still think this is a viable path forward to improve performance of asynchronous linear solvers. I think there are still tons of questions that need to be answered. But there are some initial results that suggest there is potential for improvement. So some of those questions, how does this extend to a distributed setting? Is this something that just executes in a shared memory component to a larger solver, where I trust a larger Krylov method, for example, to distribute a local problem inside of its preconditioning phase, and that local problem is the only thing that would benefit from this type of method? Is there a way to extend this method directly? It gets harder to do the randomization across nodes because you're paying an extra communication cost, which is just going to also weigh you down. How can we kind of further optimize the algorithm is really the next question. I called out using properties of the matrix, so it would be nice to look at the eigenvalues or the trace or something I can compute easily before the problem gets going. But are there ways to shape how greedy the algorithm is, how dynamic it is? Is there some way to inform what sort of parameters or what distribution should this? Is there a way to know whether a problem lends itself towards the discrete distribution, towards one of the continuous distributions, what continuous distribution, what the parameter should be, how often the problem should be updated? A lot of open questions. And ultimately, the last question is probably the most important. Is there a way to look at over a larger suite of problems on a larger set of scales whether the gain in performance is worth the extra computational overhead? So it's clear in theory that if there was no computational overhead, this would be an improved method. But in practice, it's going to be a game of balancing the benefits with the computational overhead and trying to arrive at a solver that's worthwhile. So the further investigation is kind of where we're trying to go next. So there's kind of a couple different spokes. One of them is to look at incorporating these solvers into more complex routines. There is some overhead always with changing routines inside of larger, more commercial or production scale packages. And if the rolled up benefit, not looking at the solvers directly, but inside of a practical application, is negligible, it's certainly not going to convince anyone that it's worth the hassle of incorporating these changes. To keep experimenting with different distributions, really just looking at that genericized algorithm and saying, how do I keep making this better? What can I do to improve what I'm doing? Do we do different distributions? Do we fit them differently? How do we rank the residuals? How often do you rank them? How often do you fit the distribution? Do those things have to change? How often do you need to do those things in a perfect world? We also had an idea of trying to use an evolving probability distribution. So instead of looking at creating a new distribution, essentially like refitting a distribution, is there a way to just let the parameters of the distribution shift over time, hopefully with something you know about the problem, maybe some property of the matrix or some property of the initial residual? There could be some way to say, hey, early on I want this to be more greedy, and over time I want it to flatten towards something that's more like a uniform, because I can expect that I need to make my updates to the worst residuals, in some sense, the largest local residuals, early on. I want to be very Southwell-like, but over time I'd like to worry more about the load balancing aspect of the problem. Those are really kind of the avenues for research. Practically, I think we're going to pursue trying to get some theoretical results and just new experimental results as well. So hopefully we'll have a new paper coming soon. Thank you.